let's say some function f is given. Maybe this is my function f, and it's defined on some interval from a to b, or maybe from 0 to 1. And here's how the function f looks like. And then what we did, we have defined a definite integral of this function from a to b, or from 0 to 1 of this function f dx. So remember, that was defined using the concept of Riemann sum, the idea of Riemann sum. So for example, what I could do is I could look at this interval from 0 to 1, and let's say we want to divide this interval into, let's say 1. Okay, so let's say this is 1, 2, 3, 4, 5, 6, 7. Let's say divide this into 8 equal pieces. So I'm going to say that delta x is simply b minus a. So in this example, 1 minus 0 divided by 8. So this is delta x is 1 over 8. And then what I can do, I can choose one of those three. I can do the left endpoints, I can do the right endpoints, I can do midpoints. So for example, let's say this would be on this, in this example, we are doing the left endpoint. So this is exactly this area plus this area plus this one and this one and this one, this one. This is exactly L, because we're using 11 points and the number of approximating rectangles is 8. So this is L8. Well, we could do even simpler. We could do L2, for example. So then we will divide this simply into 2 pieces, and that would be just something like that. So that's the idea of approximation definite integral. And the definite integral was defined as the limit when n goes to infinity of those left endpoints, Ln. This is the same as the limit as n goes to infinity. We can do the right endpoints, Rn, or the midpoints. So it's the same as the limit when n goes to infinity of the midpoints, Mn. And the L stands for left. And in this, what it means is, in this construction, we're taking left endpoints. And then in this R construction, we're taking the right endpoints. In M, we're taking the midpoints, and so on and so forth. So here's a very specific example. Take this function f, very simple function. It's 1/2 x plus 3. That's the function. And consider this function for x is between 1 and 7. So the domain of this function will be this interval from 1 all the way up to 7, And let's say we want to approximate the area underneath the function. In other words, let's say that we want to approximate, well, this is definite integral, one that is very simple to integrate, and we know that we could use the fundamental. But let's say, for example, I want to approximate this number. The definite integral is from 1 up to 7, of this function f. Okay, so, well, this is a very simple function, and we could evaluate this exactly, for example, using the fundamental. But let's say we want to just approximate this. So approximate this number using 3 approximating rectangles. So what I'm going to do is I'm going to say that delta x is going to be, well, 7 minus 1, and then divided by the number of approximating rectangles I want to use in this construction, so by 3. So this is 6 by 3. So that will give me what delta x is. Delta x is 2. So here's delta x. This is delta x. And so is this, because this is 2, and so is this, 2. So delta x basically is the length of the small subinterval. This is also delta x. And then, well, depending on what I want to do, if I want to do the L construction, well, then I will be using the construction L3, and L indicates that I'll be using 11 points in this construction, and 3 indicates that I'll have 3 approximating rectangles. The first of which will be this one. So I'll go, this is the first small subinterval from 1 to 3. And then because I'm doing the LF construction, I'm going to take the 11th point, which is 1, and then I'll evaluate this function at this point 1. That will give me this number. I know what the function is, so this is exactly f of 1. So f of 1, what's the formula? Is 1/2 plus 3, so this is 3.5. So this would be f of 1 times delta x. And then the same thing. This is the second small subinterval. Because I'm doing the L construction, I'll take the 11th point. So I'll evaluate this function f at 3 now, and multiply this by delta x. And lastly, the same thing. This is a small subinterval from 5 to 7. So because I'm doing the LF construction, I'm going to evaluate this at 5. So I'll give me f of 5 and then delta x. Well, but then I know what the function f is, so I can compute this number times 2. That's a delta x. This number is 4.5 times 2, and so on and so forth. That will give me 27, and 27 is the approximation. So 27 will be the approximation of the definite integral from 1 to 7, of this function f. And you can check that using fundamental. For example, you get a number that's very close to this one, this function f dx. So that was the construction L3. Well, if we can do even simpler, L1, for example, L1 would be just delta x would be 6, and we'll have only one approximating rectangle. We can do L2, so something like this, and so on and so forth. So in general, we can construct Ln, and then when I take the limit of this, when n goes to infinity, that will give me exactly the definite integral from 1 to 7. From 1 to 7 on this function. Okay, let me show you very quickly the same construction and the same function, but now I'll be using the right endpoints. So idea is going to be the same. I'll take even the same function and even the same domain. So the function is the same. Domain is also this interval from 1 up to 7. And let's say I want to use 3 approximating rectangles. And let's say I want to use now the right endpoints. Okay, so in other words, I want to construct R3. This is the Riemann sum that corresponds to this partition, and the sample points are the right endpoints in this example. So again, this is the first small interval from 1 to 3. And because we're doing the construction with right endpoints, I'll take this point 3. And then this point will give me height of the corresponding approximating rectangle. So I'll go all the way up to the function. And this number here is exactly f of what point?
Three.
Perfect. This is exactly the function f of 3. This is perfect. And so on and so forth. This is f of 3 times delta x. And then I'll do the same thing. This is the second small subinterval from 3 to 5. And because I'm doing the construction that involves the right endpoints, then I'll take this point 5. And then I'll evaluate this function at this point 5. And that will give me f of 5. And lastly, this is the last small subinterval. Because I'm doing the construction with right endpoints, I'll take this point on the right-hand side, which is 7. This point will give me the height of this rectangle, which is up to this point. So f of 7 I know because I know what the function f is, and delta x is in my example too. So that will give me R3, and what this number is, this is not exactly equal to, but approximately equal to the definite integral of this function f from 1 to 7, of this function f from 1 to 7. Okay, this the same construction with midpoints. Now when the sample point would be midpoints, I'll get, so the function is the same. Let's say that I want to use 3 approximating rectangles, but now let's say I want to use midpoints in my construction. So delta x is going to be also, this is delta x2, this is delta x, and this is delta x. And now the sample point, because I want to use m, the midpoints, then when I look at the first small subinterval, the blue one, I will take the point exactly the one in the middle. That's the sample point. And this point will give me the height of the corresponding rectangle. And then I compute the area of this rectangle, of this blue rectangle, which is this number. And then I'll do the same thing. This is the second small subinterval from 3 to 5. And I'll take a sample point to be the one exactly in the middle. So this point 4. And then I'll compute this area, because I know how to compute the area of rectangle. So compute this area that does exactly this. And then I'll do the same with the last one. Take the midpoint, which is 6 in this example, and compute this area. That will give me this number. And then when you compute this number, that will give you M3. And this would be the approximation of the area underneath the graph of this function f from 1 up to 7 using midpoints. Okay, so we did this construction, and this is the way, this is the method how we define the definite integral. So no, the graph will not be given, but the formula for the function f will be given. So for example, the formula will f will be given, but this graph will not be given on the exam. Okay, so that's a construction, excuse me, that's a construction M3. So let me review very briefly this result, which is the fundamental theorem. Okay, the fundamental basically is applicable only not to all functions, but for one that are continuous. Okay, so the situation is the following one. We have some function, and I'll be assuming that this is a continuous function, and it's a function from a to b. Maybe this is my function f. So here's a, and here's b. And the question is, how do you compute this definite integral from a to b of this function f of x dx? Well, what I can do is I can do the Riemann construction, and I can inscribe many rectangles and approximate this, and that will give me the area, because this is exactly the area underneath the function. But the question now would be, is there any method or any tool specifically that would be useful for computing this definite integral? And the answer is yes, and that's the fundamental. Okay, so the key point is to come up with the function big F. So what we do is we need to find an antiderivative of this given function f. So antiderivative of this function f is going to be a big function f with the property that derivative of this function is the initially given one. This is antiderivative of this function. Does it have to be differentiable to use FDC? Perfect question. Excellent question. See, we have two classes of functions. So one class of function is a function that are continuous. So there's a big class of continuous functions, and there's another subclass of this function that's contained inside another small important subclass of this function, and those are differentiable function. So if your function is differentiable, then it's continuous. But you might have a continuous function that is not differentiable. For example, the absolute value function. The absolute value function looks like this. It's a continuous function, but it's not differentiable. And your question was, for this theorem, does this function has to be differentiable? It's okay when it's differentiable. You can use this theorem, but even you can use this theorem at a little bit weaker assumption when your function is just continuous. If your function is continuous, you can use fundamental. So that was a perfect question. And essentially, and also, if your function is continuous, then antiderivative does exist. There's a theorem. We are using this result. We won't prove it, but we're using it. And this theorem says that when the function given is a continuous function, so maybe it's differentiable as well, but doesn't have to be. As long as it's continuous, then this big function f does exist. And the fundamental theorem will tell you how to compute this definite integral once you know one definite integral. Very simple. Simply f of b minus f of a. See, very, very deep result really in mathematics, because the whole construction is very involving. So many things to do there, Riemann sum and so on and so forth. But once you know one antiderivative of this given function f, there's nothing to do, because all you have to do is just evaluate this function f, and this is the one part of the fundamental. But now the question will be, how do you, maybe you can come up with this big function f, but if this is difficult, then one part of the fundamental theorem of calculus will give you an explicit formula for antiderivative, again, assuming that your function is a continuous one. And this is the first part of the fundamental, and it says that one big function f, in other words, one antiderivative of this function f, is given that way. This is the integral from a to x f of t dt. This function is not unique because you can integrate this from any point inside, for example, C. Take any point C in between A and B, that will give you from C to X, that will give you one antiderivative. So you see, antiderivative is not unique. This will be also an antiderivative. But then for the second part of this theorem, you can use any of those, to take any of those, this big function f, and then, okay. So very simple example, take the function integral, I don't know, maybe cosine x, and let's say, so the function cosine looks like this. This is 1, then this is 1, 2, 3, this is pi. And let's say the function cosine is like this, so let's integrate this from 0 to pi over 2. Pi over 2 cosine x dx. Okay, question for you. Is the function cosine a continuous function?
Yes.
Perfect. This is a continuous function, so we can use the fundamental. And could you give me one antiderivative of this function cosine, please? Perfect. This is very nice. So the function sine, the trigonometric function sine, is an antiderivative. And then all I have to do, once I know our antiderivative, all I have to do is I have to evaluate this function at 2 points. The first of which is going to be when x is pi over 2, when x is pi over 2, and then when x is 0. So this is equal to sine of pi over 2 minus sine of 0. And again, question for you, what is this number equal to? Sine of pi over 2 is what value?
Zero.
See, so let's recall how the function sine looks like. The function sine at 0 is like this, and then something like this, and something like this. So this is pi over 2. So sine of pi over 2 would be 1, and sine of 0 is exactly what you are saying, and sine of 0 is 0. So 1 minus 0, so this is equal to 1. Okay, very simple example, but a theorem is very important. Okay, so that's fundamental. There's 2 parts of fundamental. Basically, one part of this theorem will tell you how to compute the definite integral of a given function. So what you have to do, if the function f is given, you have to find one antiderivative, the big function f, and then evaluate this function at b minus this function at a. Okay, fundamental. And then another part of this theorem is a formula for this big function f, for the antiderivatives of this initially given function small f. Okay, so that's the fundamental. No time. So integration by substitution, very simple. Essentially, this is the same as chain rule, you know, except that in this new context of antiderivatives. So this integration is by substitution is a method, and is applicable to the following situation. When you have composition of two functions, so you have some function f, and this function is composed with some function g. So you have this situation. So for example, you have this function cosine, and the function is composed with this function x squared. But now, very important, another factor that's essential to be able to use this formula is you have to have present of derivative of the inside function. So times g prime of x, in this example, times what is the derivative of this function, 2x. But even if this is derivative up to a constant like x, for example, you can still use substitution. And in general, what we do, so dx, so in general, what we do, we said that, okay, u is equal to the function g. Then derivative of this function u with respect to x is equal to, well, we'll take derivative of this function g. So derivative of this function g, and then we have this formal step, and we think of this as multiplying both sides of this by the dx factor. That will give me that du is equal to g prime of x dx. And see, g prime of x dx, this is exactly what I have in my function. So this integral would be equal to integral f of u du. And usually the whole point of this method is this method will not solve this integral excuse me, will not solve this integral itself, but what it does is reduces to hopefully something that's easy or easier to integrate. You know, and that's essentially the substitution method, and essentially is the analog of chain rule, but in the context of math integrations. Okay, integration by parts, this is essentially the product rule. And recall that product rule is when I have two functions, one is u and one is v. For example, this could be sine x and this could be times cosine x. If this one is differentiable and this one is differentiable, then so is the product. And what does the product rule says? The product rule says the following: when you want to compute derivative of the product, this is going to be the derivative of the first function times the second function. That's only one step. And the second one is you take the first function, whatever the function might be, and you multiply it by the derivative of this function v. So when you integrate both sides, of this equation, then on the left-hand side, I'll get integral of this, and then on the right-hand side, I will get integral of the sum. Okay, but essentially, integration cancel differentiation. Essentially, this is true. So really, on the left-hand side, we have just this product, u times v. But then on the right-hand side, we know that integration is not only homogeneous operation, but also is additive, meaning that integral of the sum is the sum of the integrals. So it's going to be integral of u prime times v, and then plus integral of the other function, integral of u times v prime. And then from this, we can choose either this one or that one. So for example, I'll choose this one. So integral of u times v prime, this is going to be equal u times v minus what function? Minus this integral. Minus this integral u prime times v, and that's the integration by parts. So integration by parts is applicable to when I have product of two functions. So maybe one function is, let's say, some x squared, for example, and the other one function is maybe some sine x or cosine x, something like this. And we can choose this to be the function u, and this to be the function v prime, and then we can integrate this by parts. Following this theorem or this formula, this is really the consequence of the product rule. Okay, and I think, if I remember correctly, we actually did this example in class the other day, sometimes ago, so we don't have to do this now. But this is, so two methods only for integrations. One is u substitution, and the other one is parts. And there's no other method. Also in Math 2A, there's no other method. There's only the product rule and the chain rule, because any other is derivable exactly from one of those two. So one method for integration is u substitution, and the other is parts. There's no other method. And perfect, because now we know all of them. We know other two. So I would like to ask you to review this section as well. Partial fractions, we did this, and essentially partial fraction is applicable to what class of functions? Rational functions. So for example, I might have this substitute. This is a rational function, x squared divided by x. It's a rational function. Or I might have this function x squared divided by x squared. This is also a rational function because it's a polynomial divided by another polynomial. And also I might have 1 over x. This is also a rational function. Notice one thing. First thing to do, if I want to integrate this function, the first thing to do is I will divide, because degree of the numerator is 2 and degree of the denominator is 1. So because 2 is bigger than 1, I can divide, and x squared by x is, well, very simple, just this function. So before I integrate, and when we have this case that the degree polynomial on top is bigger than the degree of the denominator, then we divide. And for this, we have polynomial long division, and we also did this in class. When the degree on top and the bottom are equal, also polynomial long division, because this is simply 1. So in this case, when the degree of top is greater than or even equal to the degree of the denominator, then we use long division. However, when we have this situation, degree is 0, degree is 1, cannot divide because this degree is less than that one. This is exactly the situation partial fractions are applicable to. So we have degree of the denominator is bigger than and strictly bigger than degree of top. So partial fractions are exactly applicable to this case. So long division, we won't be reviewing because we did this in class, and the partial fraction decomposition here is just one example. Here's a x plus 2, x minus 1. So notice one thing, this is degree 1 polynomial, and this is degree 1, and this is 1 less, 0, and this is 0. But this is degree 2, so on top I'll put degree 1 polynomial. And that's the partial fraction decomposition, and the point is to find this a, b, c, and d. Well, for example, if this was not present, then we'll have just this. And essentially, this is the situation we'll be focusing on. That will be also very simple, but maybe a little bit tedious computations, and we don't need that. So we know pretty much everything about integrals, and let me just say 1 second kind of summary. What kind of integrals do we have? So first of all, indefinite and definite. That would be the first thing in this classification. The very basic one and the very first step in this classification of integral would be to split them into definite and indefinite. So definite and indefinite. And indefinite, this is almost the same as almost the same as antiderivative. But then definite, we have to either is proper or improper. Proper means simply that the bounds of integrations or the limit of integrations are finite numbers, not infinity. So for example, from 1 to 17, and the function is nice and continuous, well, that would be a proper definite integral. Or like in this example, from 0 from 0 to pi over 2 of this function cosine. And see, fundamental theorem of calculus is exactly applicable to this situation. I cannot apply this theorem to improper integrals. The function has to be continuous, and definite integral has to be a proper one. So I have to, the function is nice and continuous and defined over the whole domain from A to B. But sometimes what could happen is you want to integrate from, maybe from 0, and that's fine, but all the way up to positive infinity. This would be an improper integral, or you can do so the same from negative infinity up to 0. So this would be an improper integral. This is another type, but we won't be, in this class, we are not doing type 2. So I just wanted to mention this improper integral. Sometimes they're called type 1, but this is not important. So essentially, let me give you an example of this kind of situation when we have integration from negative infinity or from positive infinity. So when I have some function f, and I want to integrate this function from negative infinity up to b, from negative infinity, so from negative infinity up to this point b, of this function f, Okay, then what we do is, okay, what I can say is I'm going to fix some point t, or maybe some parameter t, which is less than this point b, and then I can look at this definite integral from t up to b, from t up to b of this function f, and notice one thing, this t is just a parameter, but it's supposed to be a number. So now what I have is I have a proper definite integral. That's just this area. This is exactly this area. It's a proper definite integral. And now what I want to do is I want to take this parameter t and push it all the way to negative infinity. And formally, what I mean by this is I'll take the limit of this expression when t, so the parameter t goes to negative infinity. Okay, and the same kind of situation when you want to integrate something from a number a to positive infinity. First of all, you focus on this definite integral from 1 up to t, and this is from a maybe up to t of this function f. And this is a proper definite integral, and that's just this area. But then when you push this point t all the way up to infinity, you take the limit of this when t goes to positive infinity. And that's how we compute improper integrals. So very quick example, 1 over x. So here's the function times it. Okay, 1 over x is the function that looks like this. This is the function 1 over x. Okay, and let's say I want to, this is 1, and I want to compute this area, this infinite area. So I want to compute this integral from 1 to infinity of this function 1 over x dx. This is what I want to compute. Is this integral proper or improper? This is going to be not proper because this is not finite number. You know, so that would be a improper integral. And how do we evaluate improper integral? When we do, we can fix some parameter t, and then I can look at this integral from 1 up to t of this function. Okay, now this is a proper definite integral. It's not equal to that. But now what I want to do is I want to push this point t all the way to infinity. And formally what I'll be doing is I'll compute the limit of this expression when t, so this parameter, goes to positive infinity. Okay, so that's just a computation of limit really, because this is equal to the limit when t goes to infinity. Okay. Antiderivative of this function 1 over x. Could you give me one? Antiderivative of this function 1 over x.
ln x.
Perfect, exactly x. And so I'll take the function ln of x. And then I'm using fundamental, by the way. So I want to see what this function is equal to when x is equal to 1. And then when x is equal to t. Okay, so this is equal to limit t goes to infinity. Okay, this is ln of t. Ln, absolute value we can skip, but ln of t minus ln of 1. Okay, another question for you. What is the function ln equal at 1?
Zero.
Perfect, exactly, because see, the function ln looks like this. This is my y-axis, this is my x-axis. The function ln of, let me call this axis t, okay? Then the function ln of t, so y equals ln of t, the function looks like this. At 1, the function is equal to 0, so this is equal to 0. But now, also a question for you. What is going on? What's happening with the function ln of t when the input of this function goes all the way up to infinity? What's happening with the function ln itself when the input goes to infinity?
Going to infinity.
Infinity.
Perfect. This is exactly what you are saying. The function does the same. When the input goes to infinity, the output does the same. So meaning that this limit is equal to, okay, so positive infinity. So this improper integral does not converge to anything. It's divergent. But let me give you another example of something that is nice and something that is convergent. For example, if you try very similar function, but try this function 1 over x squared.
Professor, I got a question.
Question, please.
So when it goes to infinity or it goes to negative infinity, then that means it's convergent?
So when you compute this definite integral, like we did,
right,
and when you get that this limit is either positive or negative infinity, it's positive infinity in this case, this means that this improper integral is divergent.
Divergent, okay.
Exactly. This is an excellent point. A very important one. I can read like that, but okay. This improper integral is divergent. However, on the other hand, when you compute this limit and you get something finite, for example, 17, that would be an example of something that is convergent. See, this one does not converge to any number. No, it just keeps going to infinity. It doesn't converge to anything. But sometimes what could happen is there's a number and you do this computation, you take the t bigger and bigger and bigger, and the function will be approaching something, will be converging something. In this case, we'll say that it's convergent. This one is not. It doesn't converge to anything. So for example, if you take this function 1 over x squared, very similar function, the difference is that the function 1 over x squared also is asymptotically approaching the x-axis. However, it does so much more rapidly than the 1 over x does. So let's say this is 1. And let's say you also want to evaluate this from 1 to infinity of this function 1 over x squared dx, and do exactly the same computation, and you will get that this is a finite number. I don't want remember now, and I want to do this computation, but you get a finite number like 1 or 3 or something. This would be an example that's improper integral, but this one is, let me just say, I can't read like that. Okay. You can do this computation later, and you will get that this limit is a finite number, and what it means is that this improper integral is convergent. Let me give you an example of something that's also convergent. So that's a function 1 over x. So we just did this. The function was 1 over x, and you took this from 1 all the way up to infinity, and you get this as infinite. So it means that this improper integral is well, I don't know how to write like this, but is divergent. But another example, we haven't done that, but you can try as an example. Take very similar function that was 1 over x, and take very similar function 1 over x squared or cubed or to the fourth. And then compute this integral from 1 to infinity, 1 over x to the fourth dx. That will be convergent. Because basically what's happening is that it does approach asymptotically the x-axis, but it does so much more faster than the function 1 over x. Okay, another example, and the last one of improper integral is, let's say we have this function. So that's the function y equals this function. And here's how the graph of this function looks like. The function will be asymptotically approaching the x-axis when x goes to negative infinity. But the whole thing, but the function will be negative. So what I want to compute is I want to compute this region. This region. So this region is simply integral from negative infinity all the way up to 0 of this function, x times the exponential, x times the exponential. So how do we compute this limit? We take some parameter t. We take some parameter t, which is less than 0. And then we look at this integral from t, so from this point up to 0. From this point t up to 0 of exactly the same function, x times the exponential, x times the exponential. This is a proper definite integral, use fundamental. And by the way, x times the exponential, what would be the best method to integrate this product of those two functions? This is a product of two functions. What of those two methods that we just mentioned, what method you could use to evaluate this integral x times the exponential as a product of two functions?
Integration by parts.
Excellent. This is exactly integration by parts. Very simple. Take u to be this function, take v prime to be this function. Super simple function to integrate. Just one integration by parts will do. And then compute the limit of this when t goes to what value?
Negative infinity.
Excellent. This is what we want in this example. T goes to negative infinity. Okay, and then you get that. See, and when you do this computation, you get that this is equal to 1. Not surprised, because the function is underneath the x-axis. It has to be something negative if it's convergent. Or maybe it has to be negative infinity, but if you do this computation and you get positive 7, this is wrong. It can't be. Even just looking at this, you can tell that this integral is going to be definitely something negative, maybe negative infinity. But then when you do computation, you get negative 1. That makes perfect sense. That should be negative. And so this one is convergent. Just see. Perfect. When t is approaching negative infinity of this exponential function. Perfect. That's exactly what you were saying. Okay, so that's improper integrals. So let me review now the last two sections. Okay, so last two things, integration area between functions. So when I want to compute this area, this would be simply the area from a to b, the integral from a to b of the top function minus the small function. That will give me the area between two functions. Very, very nice section. And really, it's fundamental theorem of calculus, because how do you compute this definite integral? Most of the time fundamental. But the interpretation of this is that this definite integral of this f minus g, that's exactly the area underneath those two functions. And last section about volume, the idea is very, very nice. So we have some function f given. This is my function f. This is my function f. And then what you want to do is you want to do the rotation of this shaded region. So you have this shaded region, And then we want to do the rotation about the x-axis, for example, or about the y-axis. Same idea, no difference. I'll just do, for the sake of example, I'll take the x-axis, and then you get something that's symmetric. So on the other side, you get something like, I don't know how to draw this, but okay, I'm not sure. So then you get something that's symmetric, and then you get three-dimensional solid. Looks like this. And then you fix any point x in between A and B. So here's A, and here's B, and you fix any point x in between A and B, maybe this point. And then you, and then what you do the cross section, which is orthogonal or perpendicular to the x-axis. So you take a piece of, so the cross section will look like this, and then like this. So the shape of the cross section is a circle. The shape of this cross section is a circle. So this is the plane that you can use to cut this solid through. Like this is the plane that you do this cross section, and then, well, what I want is I want to compute the area of the cross section that corresponds to this given point x. Well, but this is simply a circle, so this is pi times the radius of the circle, which is exactly f of x, and then I'll square it. And then the volume, very simple, integral from a to b, from a to b of the function a. Just a little bit more general situation when we have two functions. Okay, so that was the first one. So we did this example, so that was the function f, and then you did the rotation about the x-axis, you get the three-dimensional solid, you fix some point x in between a and b, you look at the corresponding cross-section, so the cross-section is a circle, compute the area of the section, and then the volume is simply integral from a to b of a of x dx. A little bit more general situation is when we have two functions. So one is f, one is a function f, and one is a function g, let's say. Well, and then let's say you want to do the revolution of this shaded region about the x-axis. So what we get is we get something symmetric. When you do the revolution about the x-axis, that was the function f, that was the function g, and that's the three-dimensional solid, the volume of which we want to compute. And we'll do so exactly in the same way. I will fix any point x in between a and b. We'll look at the cross-section. So now the cross-section, this is the cross-section, how you can see it from this point of view. But the cross-section, if this is my point x, well, the cross-section would be like two circles, one and another one. And you want to compute the area of this cross-section. The area of this cross-section, which is very simple, the big circle minus the small one. So what we do is, okay, I want to compute the area A of the cross-section that corresponds to this given point x. It's going to be the big circle, so pi times, what is the radius of the big circle? F of x, and I square it, minus pi times, what is the, now question for you, what is the radius of the small circle? This one.
G of x?
Excellent, perfect, minus g of x, and then square it, that's it. Volume integral from a to b, from a to b, a of x dx. Example, take one function f to be this function. So that's the function y equals square root of x, and take another function g to be the function y equals x squared. Okay, so now I have two functions, square root of x and x squared. First question is, I want to see and I want to know for what value of x those two functions are equal. And notice one thing, square root of 1 is the same like 1 squared. So when x is equal to 1, those two functions are equal. Okay, so this is the region. Now what I want, what I want to do is I want to do the revolution of this region, and again, either about the x-axis or about the y-axis, same idea. So I'll do just, for example, about the x-axis, and I'll get the three-dimensional solid, the volume of which I want to compute. So again, I'm going to fix any point x in between 0 and 1, and then this is my point x. Okay, and I'm looking at the corresponding cross-section. So the cross-section is like one circle minus another circle. So this is how the cross-section looks like. So the area of this cross-section, let me just admit this person. Admit. The area of this cross-section is a function of x. Because while we'll be moving this x to the left to the right, the area will be changing. So this is the big circle, which is pi times the radius. Okay, what is the big radius? From here to here. So what is the first radius?
Square root of x.
Excellent. Square root minus pi times. Okay, the small radius is, of course, this one, but the function is x squared. Okay, square it, and finally, volume of the solid is integral from 0 to 1 of pi times, let's see, this is square root of x, and then the square root, that will give you x minus pi times x squared, and then squared, so x to the 4th. So integration is a homogeneous operation, so it's pi times the integral from 0 to 1. And then I have this function x minus x to the 4th, and it's a simple function to integrate because it's essentially just a polynomial. So that will give me 3 pi over 10, and that's the volume of this three-dimensional solid. So essentially, differential. Okay, so one thing very important, what I would like to ask you to review, I have not mentioned it here, but it is the mean value theorem. Essentially, the mean value theorem is to do the average value of a function. Average value of a function. So if a function f is given, the average value of this function is simply integral from a to b of this function f dx divided by b minus a. And then, so we did this in class, I'm not being specific now, but I would like to ask you to review the average value of the function and the mean value theorem for integrals. And we also did this in class. So I think that's all what I have to say for today, because we have no time for differential equations. So let me just get back to the very first slide that we just mentioned. So essentially, the exam will be from section 5.1, area, distance, definite integral, fundamental theorem of calculus, U substitution, integration by parts, partial fractions, integration using tables. We don't have to absolutely memorize all of those. Improper integrals, area between functions, average value of the function, and the mean value theorem, and then volume. So essentially those things. So let's say we won't be including differential equation because we have time for this, and we'll be doing this in just a well, you don't have to draw the functions, but you will have to find the point when those two functions intersect. And the reason for that is because you will need to know the bounds of integration. Well, essentially 7.1, let's say, essentially, I would like to ask you to very briefly review this section 7.1 very briefly, but don't worry about this section too much because we won't be asking you about differential equation because that was new. So let's say that we will do from 5.1 all the way up to volume, and including volume. Volume will be important. The volume, definitely. The section about volume, yes. The section about the volume, which is section 6.4, yes. And then the average value of a function and the mean value theorem for improper integrals. So very quick reminder, when you have a function from A to B, and you have a function f. Okay, then the average value of this function is very simple. It's just definite integral from A to B of this function f, of this function f of x dx, divided by b minus a. So let's say, for example, you have a function from A to B. Maybe the function looks like this, and maybe it's from 1 up to 7. And let's say, for example, that the average value of this function, f average value of this function is equal to, for example, 3. Then you can, just knowing the average value, you can compute the definite integral from 1 to 3 of this function f. And we did something like this the other day. Okay, so that's all what I have to say for today.